All right, we're going to dig a little deeper into frequency response now. So suppose we have a underdamped second order system. Uh, we look over here, the static gain would be K. So we make the transfer function. So this becomes S squared, that becomes S, no S here. Then we would have y of S over x of S is K omega n squared over S squared plus 2 zeta omega ns plus omega n squared. We're going to evaluate this thing a little bit. All right, the poles are located at minus zeta omega n plus or minus omega n, then we have the square root of 1 minus zeta squared. Now we'll notice this whole term right here is equal to the damped natural frequency. We've already discussed that. And that's the frequency of oscillation if you apply, say, a step input. It's the natural frequency this thing wants to oscillate at. Okay. Then we have, of course, this is the real part. So 1 over zeta omega n is the time constant, and we can get settling time and all those wonderful things. If you let s go to 0, you're left with k is the static gain. We're going to let k equal 1. All right. So what I want to do now is start to look at if we were to think about plotting the frequency response. So in the last problem, we took a look at a system, we checked out the magnitude and phase at 4 radians per second. But what we want to get to is where we could plot this for any frequency. And so basically computing magnitude and phase at lots of frequencies. And there's some structure to how this works. So that's what we're going to start trying to look to find. And so when you go to do one of these plots, the first thing you might want to check out, well, what about omega equals 0 radians per second? So that's the DC frequency. So what would one do? Here we have this thing over here. We have transfer function, magnitude is a function of frequency. The top, we let k equal 1. So this has the magnitude on top is just omega n squared. The phase is 0. All the actions on the bottom. So we go and let s equals omega I. Well, if we do that, okay, we have a mistake in here. Let me take care of that. There we go. So we let s equal omega I. We square that. We get minus omega squared plus 2 zeta omega n. And now here's that s, omega I, plus the omega n squared of the n. So you're getting the magnitude, you're going to pull the terms together. So we take the terms that are real, we square that. We take the term that's imaginary, square it, take the square root, so on and so forth. And here's what you see. If we let omega equal 0, what are we going to get? Well, that wipes out that term. It wipes out that. We're left with omega n squared over omega n squared, which is 1. Okay, so for low frequency, transfer function magnitude here is 1. And if we check the phase, so what do we have? The phase in the top is 0, 0 minus. Now the inverse tangent of what's down here. Here is the imaginary part, 2 zeta omega n times omega, divided by omega n squared minus omega squared. And now we're going to say, well, let omega go to 0. Well, that's going to wind up with 0 on omega n squared. And so that's 0 degrees. So we're starting from a gain of 1 and a phase of 0. Now we're going to go to what's called the natural frequency. And we'll see a certain pattern that happens with that. So here's the transfer. If we go to get the phase, I'm not going to bother computing the magnitude here because there's a few issues here that we're going to wind up talking about. But omega n is in the region of the resonance, which is where the amplification is generally more than 1. So the magnitude is generally more than 1, but it gets very involved, and we're going to deal with that later. I'm just going to deal with the phase. At the natural frequency, this is what really the natural frequency means, is that if you go to take the phase, so you let s equal I omega n. Okay, so you can picture putting that in here, omega n squared. Well, this is with minus omega n squared. If you put that in, ooh, you get a 0 on the bottom. And then you put omega equal omega n squared, you get 2 zeta omega n squared over 0. So this is the y portion, this is the x portion, and you got this minus sign over here. So this is minus 90 degrees. This piece here would be 90, and then you add the minus in, and that comes over. So here's the thing. For every power of s, we have 2 of them. Your phase will shift by 90 degrees. Since it's in the bottom, you'll lose 90 degrees of phase for every power of s. At the natural frequency, you exactly lose half of that. So it's for an underdamped second order system, this is the place where the phase is minus 90. Okay? This is always true. All right? So now we're going to go to, now the gain, we'll talk about that in just a moment. And we're going to get into it pretty deep. Let's look at high frequency. So you let omega equal infinity. We stick that in there. Okay? And I have that here. What you have if you start canceling terms and whatnot, this should be omega n. There we go. This is basically one level of infinity, and omega n squared relative to infinity squared is nothing. So if you cancel out an infinity, basically what you have here is the minus inverse tangent 1 over minus infinity. Okay. This is the definition. This is 180 degrees minus. So we're at minus 180 degrees. And so what did I say? For every power of s, you have a phase shift of 90 degrees. So two powers means 180. Since this is in the numerator, you lose 180. Now, if we were to do a plot of what we found, this is what you would find. Okay? At low frequency, you go down near 0. At omega n, you exactly lose 90, and at high frequency, you lose 180. And then this would just go on forever as frequency keeps getting higher. All right? And this would just work its way down to 0. On the gain side, there are 3 frequencies that are all kind of close to each other. The natural frequency, the damped natural frequency, and the maximum, omega max. Okay? Omega n simply means the place you lose half the phase. Omega d is when you go to solve the differential equation, it is the frequency the system naturally wants to operate at as it attenuates and reaches steady state. So we'll see one of those things. We'll solve this stuff in a little bit. Omega m, okay, this is a resonance, which means in this region, you have an input sinusoid, the output is magnified, so the gain is more than a factor of 1. The point at which this hits the maximum is omega m. Now, and these are all generally kind of close to each other. And in fact, if your damping is 0, they're all at the same spot. Okay? So what we need to start talking about now is put a little thought into how these all interplay, or these 3, relative to this peak. So that's what we're going to take a look at next.